Sound and light waves. Sound waves are defined as a form of energy which produce the sensation of hearing. What are the properties of the sound waves? Properties can be given as following. The first one is that sound waves are longitudinal in nature. Second, it requires a material medium for its propagation. They can be deflected from any medium. They suffer from diffraction. They also show the phenomena of interference. They have the property of diffraction as well. Sound propagates with velocity much smaller than the velocity of light. The sound gets absorbed in the medium through which it passes. Now let's go to the loudness or intensity of sound. The loudness is directly proportional to the log of intensity. So, the loudness is equal to K log to the base 10. Now here K is a constant. Of proportionality. The unit of sound is BEL. The relation between intensity and amplitude is given by that intensity is directly proportional to the square of the amplitude. The relation between intensity and distance from the source is given as intensity is inversely related to the distance squared. What is pitch, or you can say shrillness of a particular substance? Pitch is a sensation which determines the shrillness of a sound. It is subjective and cannot be measured. It depends upon frequency and its relative motion between source and listener. Quality and timbre. Quality is a characteristic of musical sound which enables us to distinguish between two notes of the same pitch and loudness produced by two different sources. Now, moving on to the velocity of longitudinal wave, denoted by U. We can also say it as Newton's formula. The relation is given as U is equal to square root of E divided by rho. Here E is the coefficient of elasticity and rho is the density of a particular medium taken into the consideration. Velocity of sound in solids. Velocity of sound in solid is given as here y is Young's modulus of elasticity and rho is the density of a particular medium taken into the consideration. In liquids, is given by U is equal to square root of B divided by rho. Here B is bulk modulus of elasticity and rho is the density of the material in the consideration. Velocity of gas in it is given as U is equal to square root of gamma P divided by rho, where gamma is Cp divided by Cv, which is the adiabatic ratio where there is no exchange of heat or energy. P is the pressure and rho is the density. Now, what are the various factors affecting the velocity of sound? Let's see the effect of density. The velocity of sound in gas varies inversely to the square root of its density. The relation can be given as u1 upon u2, which is equal to the square root of rho 2 by rho 1, considering two substances, that is the sound and the particular medium, for the effect of density. Let's see effect of moisture. It is given as velocity here in moist air divided by the velocity in dry air is equal to the square root of density in dry air to the density in moist air. This signifies that sound travels faster in moist air. Effect of pressure. Effect of pressure is given as velocity of sound is equal to the square root of rho p divided by gamma p divided by rho, which is also equal to gamma k, where is k the constant of pressure divided by rho, and it is constant. This signifies that the pressure has no effect on the velocity of sound. Effect of temperature. It is given as here the relation shows that the velocity of sound varies directly as the square root temperature on Kelvin's scale. The temperature coefficient of velocity of sound. Which is denoted by alpha, is given as u0 upon 546, which is equal to ut minus u0 divided by t. overtones in an open pipe. A pipe is open at both ends and therefore the air is free to vibrate at any open end. We must get an antinote at the open end. Now, in the first diagram, this is the length of a particular pipe. This is node. That is lambda 1 by 2. We are getting 2 antinodes. This is lambda 1 by 2. Sorry, 4. This particular part, that is lambda divided by 2. Again here we get lambda divided by 4 as this particular overtone is half. Going to the figure 3. Now, what is fundamental frequency? Fundamental frequency, here the wavelength is given by lambda is equal to 2L. Is given by F is equal to velocity divided by 2L, which is also equal to 1 upon 2L multiplied by square root of rho P divided by gamma P divided by rho. Now here L is the length of the pipe and U is the velocity of the sound. Going to the first overtone. Or you can say it as second harmonics. It is given as the wavelength is equal to 1 and the frequency is 2f. For the second overtone, the wavelength is given as and the frequency is given as. The second overtone is also known as third harmonic. Overtones in a closed pipe. Since air at a closed end is not free to vibrate, there must be a note at the closed end always as shown in the figure. Consider this as the length of the pipe. This node is half, therefore it is lambda 1 by 4. This is a full node, that is, it is lambda 1 divided by 2. Same goes over here. For this, the fundamental frequency is given as the wavelength is lambda is equal to 4L and the frequency is F is equal to U, that is velocity divided by 4L, which is also equal to L is the length of the pipe and U is the velocity. First overtone. Or you can say third harmonic. Here the wavelength is given as lambda 1 is equal to 4 by 3 L, that is the length. Frequency is given as F1 is equal to 3F. For the second overtone, that is also known as fifth harmonic, the wavelength is given as 4L upon 5 and the frequency is F. Now let's compare the fundamental frequency of closed end pipe with open end pipe. The relation is F is equal to 2F, that is frequency is equal to 2F. Moving on to Doppler effect. The apparent change in pitch of note due to the relative motion between the source and the listener is called Doppler effect. The example can be taken of the whistle of a train, which the voice fades away when the train moves more far away from the listener. Now, consider that source is in motion and listener is at rest. First case we can take as the source is approaching the listener. The modifying wavelength would be lambda is equal to V minus A divided by F. The apparent frequency, that is F dash, will be V divided by V minus A upon F. The change in frequency, that is delta F, would be given by A divided by V minus A upon F. Here V is velocity of the sound in air and A is velocity of source when it moves toward the listener. Consider case 2. When the source is going away from the listener, here the apparent frequency, that is F dash, is given as V upon V plus A F, and the change in frequency, that is delta F, is minus A upon V plus A upon F. The case 3, when the source is crossing the listener, that is, we can consider the source is passing by a listener and the apparent frequency of source before crossing is given as V upon V minus A divided by F. The apparent frequency of source after crossing is given as V upon V plus A multiplied by F, and the change in frequency is given as minus 2AV divided by V square minus A square multiplied by F. Now, when the source is at rest and listener is in motion. Now your case 1, when the listener is moving away and the apparent frequency f dash is given as v minus b divided by v multiplied by f. The change in frequency is given as delta f is equal to minus b divided by v multiplied by f. Your b is the velocity of the listener. Case 2. When listener is moving towards the source, here the apparent frequency is v plus b divided by v multiplied by f, and the change in frequency is given as plus b divided by v multiplied by f. Now here the case 3, that listener is crossing the source. Now the apparent frequency before crossing is given as v plus b divided by b multiplied by f, and the apparent frequency after crossing is given as v minus b divided by v multiplied by f. The change in frequency now can be given as minus 2fb divided by v. When the source and listener both are in the medium, change in frequency due to relative motion of source and listener can now, when the source is moving in this direction and the listener is also moving in the same direction, the nature of velocity is that both are positive, and the expression for apparent frequency can be given as v minus b divided by v minus a multiplied by f. Now when the source is moving in this particular direction and the listener is moving in this particular direction, the nature of velocity is positive and negative respectively, and therefore the expression for apparent frequency can be given as v plus b divided by v minus a multiplied by f. Now when the source is moving in this particular direction and the listener is also moving in that direction, the nature of velocity is negative for both, and the apparent frequency is given as v plus b divided by v plus a multiplied by f. When the source is moving in this direction and listener is moving in this direction, the nature of velocity is negative and positive respectively, and the apparent frequency can be given as v minus b divided by v plus a multiplied by f. Now, what is the effect of motion on medium? The frequency, that is f dash, is given as r minus b divided by r minus a multiplied by f. Now here r is v plus omega cos theta and omega is the velocity of wind. theta is the angle between direction of propagation of sound and that of the wind. Going to Huygens principle. The wavefront of a wave at any instant is defined as the locus of all the particles in the medium which are being disturbed at the same instant of time and are in the same phase of vibration. Now let's consider point A, that each point on the wavefront acts as a source of a new disturbance and emits its own set of spherical waves called secondary wavelets. The secondary wavelets travel in all the directions with the velocity of light so long as they move in the same medium. This is wavefront 2 and this is wavefront 1, and these dots are the points of wavelet source. Consider point B, where there is only wavefront 1 and these are the wavelet source points. In the diagram B, the envelope or the locus of these wavelets in the forward direction gives the position of new wavefront at any subsequent time. Let's go for the determination of phase difference. The phase difference between two waves at any point will depend on, number 1, difference in the path lengths, of the two waves from their respective sources. Second point, refractive index of the valley of the medium. Third point, initial phase difference. Fourth is the reflection, if any, in the path followed by the waves. Now moving on to the reflection of a plane wave at a plane surface. That is, we can also say laws of reflection. First thing, the incident ray, the reflected ray and normal to the reflecting surface at a point of incidence all lie in one plane, and that plane is perpendicular to the reflecting surface. Second point, the angle of incidence is equal to the angle of reflection. This signifies angle of incidence is equal to the angle of reflection. Now let's go on to the diffraction of light. Diffraction is the phenomena by virtue of which a wave going from one medium to another medium undergoes a change in velocity. Consider the following diagram. Now, this is the incident ray and this is the refracted ray. First point, the sign of the angle between the incident ray and the normal bears a constant ratio to the sign of the angle between refracted ray and the normal. It can also be given as sin I by sin R is equal to V1 by V2, which is a constant. Here V1 and V2 are the velocities in velocity of sound in first and second medium respectively. Mu1, mu2 is refractive index of the second medium with respect to the first. Second point, the incident ray, the refracted ray and the normal to the refracting surface lie in the same plane. That is, incident ray, refracted ray and normal are in same plane. Now to the phenomena of interference. Interference is the modification in the distribution of light obtained by the superposition of two or more waves What is the principle of superposition? The principle states that number of waves traveling simultaneously in a medium behave independently of each other, and the net displacement of the particle at any instance is equal to the sum of individual displacements due to all the waves. The displacement equation is given by y is equal to r sine 2 pi divided by lambda multiplied by Vt plus x upon 2. The amplitude is given by r is equal to 2a cos pi x by lambda. The intensity is given by k4 alpha square cos square pi x divided by lambda, where intensity can also be kr square. Maxima. It is a point having maximum intensity. It is given as x is equal to 2n lambda divided by 2. A point will be a maxima if two waves reaching there will have a path difference of even multiple of lambda by 2. It can also be given as Imax, which is equal to 4k alpha square, that is 4I. If we consider I is equal to k alpha square. Minima. It is a point having minimum intensity It is given as x is equal to 2n plus 1 lambda by 2, and a point will be a minima if two waves reaching there have a path difference of odd multiple of lambda by 2. It is given as I minimum is equal to k multiplied by 4a square into 0, which gives the final value as 0. Now moving on to the condition for constructive interference. The path difference for the constructive interference is given as 2n plus 1 lambda divided by 2, and the phase difference, the path difference is given as 2n lambda by 2 for the constructive interference, and the phase difference is given as 2n divided by pi. The condition for the destructive interference is as follows. The path difference is given by 2n plus 1 lambda by 2, and the phase difference is given by 2n plus 1 divided by pi. Now what are the coherent sources? The coherent sources are the sources which either have no path difference or you can say the phase difference, or have a constant difference of phase between them. What are the conditions for interference? The first one is the two sources should emit continuously waves of same wavelength. Second point, the amplitude of two waves should either or nearly be equal. The two sources should be narrow. The sources should be close to each other. And the last one, the two sources should coherent each other. Going on to Young's double slit experiment. The path difference here is given as x is equal to y d by capital D. The maxima here is y is equal to n lambda capital D divided by small d, where n has the value of 0, 1, 2, 3, etc. The minima is given by y is equal to 2n plus 1 lambda capital D by d. Here the n values are also 0, 1, 2, 3. Moving on to fringe width. It is the distance between two consecutive bright and dark fringes. It is given as beta is equal to lambda capital D by D. The displacement of fringes due to introduction of a thin transparent medium can be given as when the shift for a particular order of fringe is delta y is equal to beta divided by lambda multiplied by u, that is velocity, minus 1 divided by t, that is time taken. B. The shift across a particular point of observation is given as for Lloyd's single mirror, the change in lambda is given as beta multiplied by 2 alpha upon d. The power of lens is given by formula 100 divided by f, that is the focus. The magnifying power of simple microscope is given as m is equal to 1 plus d, that is distance, divided by focus. The magnifying power compound microscope is given as m is equal to L divided by f0 multiplied by 1 plus d upon fe, where f0 is focal length of objective and fe is the focal length of eyepiece. L is the length of the microscopic tube. The magnification of astronomical telescope in normal adjustment is given as m is equal to f0 divided by fe. The magnification of astronomical telescope in final image is formed at the distance of distinct vision is given as m is equal to f0 divided by fe multiplied by fe plus d divided by d. The magnification power m of Galileo's telescope is f by f, where the focal length of objective is divided by the focal length of the eye lens. Moving on to the phenomena of diffraction. Diffraction is bending or spreading of waves that encounter an object that is a barrier or an opening in their path. In Fresnel class of diffraction, the source and or screen are at finite distance from the aperture. In Fraunhofer diffraction, the source and screen are at infinite distance from the aperture. Fraunhofer case is a special case of Fresnel diffraction. Polarization the polarization of two interfering waves must be same state of polarization or two sources of light should be unpolarized. Going on to the Brewster law. According to this law, when an unpolarized light is incident at polarizing angle, that is I, on an interface separating a rarer medium from a denser medium, of refractive mass is such that mu is equal to tan I, then the light is reflected in the rarer medium is completely polarized. Reflected and refracted rays are perpendicular to each other. Going on to reduction in intensity. Intensity of a polarized light is 50% of that an unpolarized light. That is, where IP is intensity of polarized light and IU is intensity of unpolarized light.